before we get started, can I see how many people are familiar with like macOS reverse engineering or like privilege separation? Is that nobody? Okay. I see one. Okay, cool. All right. The agenda, essentially, I'll start with an introduction of essentially covering who, when, what, and why. Then I'll move on to 3 bugs, the first one being ZCC LPE, and then an AWS VPN local privilege escalation, and then a installer local privilege escalation. And then essentially I'll cover 2 bugs that I thought were interesting that I couldn't necessarily exploit to achieve code execution as root, but they're still logic bugs. Cool. I'll start with the who. I'm a security consultant at WithSecure. I have to have this obligatory, my opinions are my own and don't represent my employers, even though that doesn't actually cover you, but still. Primarily, I have responsibilities with like operating system security, build reviews, thick clients, NetSec, code review, etc. And of course, the necessary evil of writing reports. I have some certifications, not that certs really mean anything. I've spoken at some conferences before. This is definitely the biggest conference of them all. I did some bug hunting and I found some bugs. Cool. Start off with the when. This was like a period of like 2 months where I maybe spent an hour a day, give or take, like 60 hours, 65 hours finding bugs. A lot of the bugs are just like typical TCC bypasses, but I thought these 3 bugs were particularly interesting and like could help other people to learn about this kind of stuff. Mention to WithSecure Labs. WithSecure Labs is our like research group, and we publish our research at labs.withsecure.com. The value of like disclosing bugs is not just for the people you're disclosing the bugs to, so they can fix their stuff. It's also for other security researchers, so they can learn about the bugs, how they can find them elsewhere. Yeah, check out this in the coming weeks, and there'll be 2 blog posts in more depth than I'll cover today. What actually is a logic bug? I'm essentially preaching to the choir here because there's like a lot of security people, but essentially logic is reasoning conducted or assessed according to strict principles of validity. Essentially, logic bugs have high exploit reliability, so it's not something like memory corruption where you could like break a device or cause an app to crash. Essentially, it's breaking trust placed on processes and procedures. Essentially unverified assumptions and things like file system operations, link-based abuse, coercion of like privilege execution of controlled resources, and like crossing privilege boundaries through like unexpected manners. Essentially we can assume this file exists, or the client is going to be trusted is signed by us. Why these bugs still exist? This is not new research. Like people like Csaba Fitzel and Wojciech, they've spoken at conferences, very similar bugs, and you can still find them in like modern applications. A lot of the time when you see a talk or you see a blog, it's the process of just the successes, not necessarily the failures. So it's sometimes useful to see that kind of thing so you can build like a mindset. I wanted to cover that like story of walkthrough of how I identified some of the bugs and like how you can build a methodology or automate steps to make your life easier. And the responsible disclosure process is a little bit annoying when it comes to like HackerOne, BugCrowd, etc. But I'm not going to, drone on about that. Come talk to me and I'll maud about it. Cool. To start, ZCC, local privilege escalation. Essentially, it's a cliche NSXPC bug where you can abuse like an entitlement placed on an executable, get code execution within the executable that has the entitlement placed, talk to an NSXPC service and get root, but cool. So this kind of adventure started with a client project. Essentially, it's a piece of software which allows you to like connect resources together. So a user doesn't want to run a VPN, they just want to connect to a specific resource like internal GitHub or GitLab, etc. You install this ZCC connector and it allows you to talk to that stuff. A client came to us asking, we've got this app, it has posture policies, it forces like BitLocker, antivirus, specific certificates installed. Can a user from a third party bypass this if they have it installed on their device? I was like, cool, you're paying us to do crack me's basically, which is fun. They had 5 days on Windows, 5 days on macOS. I was the person that did both. I demonstrated all of the POCs. I had like full posture bypasses in a couple of days, which was fun. So I had some extra time to give them some value. Like, are they at risk? Can somebody with a foothold on the device get code execution as root? I immediately, like Windows was relatively hardened. There's a lot more people that have looked at Windows reverse engineering, Windows vuln research, and macOS is like kind of a bit of a gray area. People don't fully understand it. I found a couple of components which were like, this isn't good. Let's like pull the string and see where it goes. Yeah, I found some bugs. So to start off, when you're like looking for exploiting from a low priv user to a high priv user, you kind of look at what's available, what's running, what are the privileges it's running as. So you can see like when you run the processes command, that's an alias. You see two components running as root. You can also see some launch daemons that are running. So you see within launch daemons, there's two components related, service.plist, tunnel.plist, and then you can also see the launch daemons loaded and like actually with a PID with launchctl. Actually looking at those plists, you can identify like what components are running, like where the actual binary is. Does it have any way you can communicate with it? That's Mac services and program arguments. You could essentially see this com.zscaler.service tray communication. So that's the thing you can talk to. You can do the same for the tunnel component. You see the same thing, the Mac service and the program arguments. Before I continue, quick little intermission about SIP, system integrity protection. On Windows, you can essentially just open a process if you have permissions to do it, essentially allocate memory right to the memory, create a thread, and you're running in the process space of that executable. You can't do that on macOS, like unless you have a 0-day or you have something that you can like leverage. You can't do like DLL hijacking, DLL sideloading, planting, all the fancy terms that people like to use. You can't attach a debugger to things unless they disable security features or through vulnerable entitlements. So essentially, inspecting these components with the CodeSign util, you can essentially see the top left is the Zscaler executable itself, the like main GUI app. No interesting entitlements like, yeah, the Zscaler service, nothing really of interest. However, this tunnel component had two things that are very interesting. The com Apple security CS allow dialed environment variables. So you can set an environment variable that equals like your dilib, and then it will load it. However, because of the hardened runtime, it won't load it, it will just refuse it. And that's where the disable library validation entitlement comes in. So now you have a way to load code within that specific component. You can automate the steps. You don't have to run those like CodeSign commands each time. You can use Yara. Yara is amazing. Like from threat intelligence, threat hunting, everybody loves Yara. You can essentially use the Yara rules at this gist and essentially find that specific binary. You can scan your whole system and find loads of fun stuff. So NSXPC, essentially the newer spec, the higher level API, is based on XPC, which is essentially a framework, literally like IPC for Windows. It allows multiple components at multiple privilege levels. They can be the same privilege level to talk to each other. They have interfaces, connection objects. They have a listener. They essentially facilitate connections between multiple components. So essentially, in order to talk to these, you need to read the documentation to understand how to speak the language. So this here specifically is NSXPC. You essentially initialize a connection, tell it what object you want to, what language you want to speak, resume to it, and then essentially, yeah, you can talk to the service. So you see on the top right, that's the reversed Zscaler service binary. It has the connection string com.zscaler service tray communication, and then the bottom left, you can see it's just essentially the frame of how to talk to it. I haven't told it what we want to connect to though, so it's just a starting point. Doing some more reversing within the should accept new connection like handler. There's three main components. You can either talk to the actual Zscaler like endpoint, which is for the tray, aka the user interface, or you can talk to essentially the tunnel or the filter. So essentially, because we'd found the tunnel component had the vulnerability in it that you could load code, we want to inspect that more. So if anybody's familiar with like iOS, like reversing, you can use something called class dump, or IPSW is like another tool. I had a really weird bug with class dump, which I didn't understand, that essentially it couldn't load the classes despite it being Objective-C. And as you can see here, it says it's Objective-C, but it didn't work. So luckily in a blog, I found somebody mentioned something called class dump Swift. And for whatever reason, it wasn't written in Swift, it was written in Objective-C, but I could dump classes. So you see these classes are like what's actually available through the XPC service. So you see things like stop tunnel and start tunnel, things like clean logs, update config. These are things that could be interesting to abuse. Like you might want to like delete files or essentially completely deny service to the user. Another interesting component was the actual Zscaler tunnel. That's like another component you can talk to. The XPC protocol itself had far more functions. It had a total of 53 functions which were available. So essentially it's a case of identifying the ones that are interesting and just manually reversing it. It's horrible work, but you find fun stuff. So immediately I found some interesting things like update external proxy config, clean up DB files, and there was one function called install revert ZCC, and software installation as root that you could potentially control. Sounds like a path to get root code execution. So you see there's references to like architecture strings, things like x86, 64, ARM64. There's a mention of a path inside the debug string. Seems like we're getting warmer. There's a subcall to a function called install ZCC with racks, which is essentially like the path you specified. Reversing the install ZCC function, you see it's just appending arg2 plus this known string, the contents macOS install builder. And if you know macOS, when you reverse like a .app, I mean, you like open up a .app, like show in the Finder, you see the contents macOS directory, which usually has a binary within it. So we know we now can control the argument, which is like a path. We have nice debug output for debugging, which is just written into like known file paths within like the logs directory. And it calls run command to shell. So seems like a good primitive for local privilege escalation. As I said before, the top screenshot shows that like initial frame to talk to the actual service, and the bottom right just essentially just creates a remote object proxy and essentially sends the temp directory, and then essentially if we place that contents macOS install builder, it gets executed as root. So that's easy code execution. Probably took about an hour and a half to find, which was super easy. This is like a multi-billion-dollar company. A dangerous assumption was placed. Assuming we, an attacker, cannot load code into a signed macO executable and then talk to the XPC service, and we broke that assumption. Cool. Second bug I'm going to talk about is a bug in the AWS VPN. The AWS VPN is a traditional VPN. Essentially, it takes a config and then sets up a new network adapter and allows you to talk to resources. Instead of NSXPC, this time it's an XPC, so it's like a lower level API, far easier to reverse, far easier to understand. So what is the AWS Client VPN? It's essentially just a wrapper around an OpenVPN build that has some things like hardened. So if anybody's like exploited OpenVPN, if it's like running in a privileged component, you can set like scripts to run before and after the VPN goes up and down. They completely patch that out, which is good. It used a privileged helper tool, so you didn't have to type in your root password every single time. So you just click a button, connect, disconnect, and it does root stuff. So you see, yeah, turn on and off the VPN, reset DNS settings, etc. It empowers the user, allows the user to do things that they would need a password for. So doing some reversing, quick little triage using the symbol dump tool, you can immediately see the XPC underscore functions. That's the C API instead of NSXPC. Doing some further reversing inside the main function, there's no immediate verification of a client. So essentially there's nothing. Then it has a XPC peer event handler with a bunch of message types. Ignore the top ones. There's a restore DNS, fix DNS, and uninstall. So you just need to like follow the thread, keep on pulling, see where you end up. No verification. There's literally nothing to verify that the client connecting is who it's supposed to be. So looking at the fixed DNS functionality, you see the applications directory is used. Essentially, you call that function with the correct message type, and it essentially runs that script in that hard-coded path. Okay, cool. That directory has been changed to be root because it contains a privileged helper tool. The permissions, we can't do anything with that immediately. Same with the restore DNS. It's calling a hard-coded script content. It's using poppin instead of the Objective-C methods. However, inside the uninstall application function, it uses remove item at path, and it's deleting inside the applications directory. It's also deleting the AWS VPN client directory in its entirety. So the scripts we saw before, so it's running from AWS VPN client. We have the ability to execute that script, and now we can delete it. So if we potentially deleted it and then called the script, maybe ideas. So essentially, you can start up a connection using the CXPC API and essentially start a communication to that service. And then you can just make your directory. So you essentially call the uninstall message, create the exploit directory, and then because it's macOS, inside the applications directory, you don't need to be root to install apps. If you use Mac, you can just drag the app onto that little window that pops up and it installs it. You don't need a password. So we've created that directory, create the script in its place, and then call the fixed DNS or the other DNS function, and then get code execution as root. Another super simple bug in these bugs still exist because not very many people have laid eyes on like macOS apps compared to Windows. Like everybody in the NAN knows Windows. A dangerous assumption was placed, assuming us, an attacker, wouldn't connect to an XPC function. Wouldn't connect and call an XPC function. They were an amazing company to work with when I reported the bug. I just sent them an email, got their GPG key, sent them the write-up, and then like within a day they got back to me, and then like within a couple of weeks they'd fixed it. And they did the fix amazingly. They essentially enforced an identifier check. Is the person who's connecting who it's supposed to be? They essentially set the code signing ID to be the correct code signing ID for them. It doesn't use the PID. You can't abuse it through PID reuse attacks, and rejects it if it fails. Really good. Well done, AWS. Cool. I'm going to now talk about a installer bug. So typically when you think of like local privilege escalation bugs, it's more of like you like land on a box and you want to get to root. With these kind of bugs, if you can like anticipate software installation or anticipate software updates, you can essentially either place files, create directories, redirect privilege operations. On Windows, it's not so much of an issue. On macOS, they like explicitly say these are bugs, which is super interesting. Because you do see on like Windows MSI files, you see people get like privesks through installers, and it's like 50-50. People think it's a vuln, people don't think it's a vuln. It's interesting. Cool. If you're interested in like installer bugs, I highly, highly recommend this talk by Patrick Wardle. It's amazing. Him and the Objective-C group got some really good research. A quick little talk about installers. There's like two main types of installers. There's package installers, app installers. There are other types, but just for sake of ease, these are the main two I'm going to talk about. With package installers, you need to install it. You need a root password. It's a bit more annoying. With app installers, as I said with the previous bug, you can just drag and drop install. You can also ask for elevation with the SM jobless API, but I'm not going to cover that here. With the package installers that ask for the root password, it has a pre-install and a post-install script, and these get executed pre-install and post-install. So you have different stages where you could potentially abuse something. Package installers, as I said before, they're typically elevated, so you need a password to double-click it and install it. An interesting thing, if you know with like Windows, if you ever do like operating system security, you see path hijacks very frequently. So like a client will have added like the D drive to the start of the system path, and it's like great, the D drive can be written by anybody, any other like scheduled task or like another binary with like not full path, fully qualified paths. You can just plant the binary there. The scheduled task will just execute the one you planted. Same kind of thing happens on macOS. By default, the user local bin directory is writable by users in the admin group, which is not amazing because if a root script is running something from the admin group, from a directory that's owned by the admin group, you can get code execution to root without a password. Yeah, it's fun. So when you're like looking at installers, there's a piece of software called suspicious package, which is adequately named. Essentially, it allows you to like inspect subcomponents. So either you think something's malware, or you might want to look at it for like exploitation opportunities. You can just drag and drop it onto this piece of software, read the code. It's annoying, it doesn't have syntax highlighting, but you just Command A, paste it into like Visual Studio Code or something like that. So essentially, the pre-install script is what I'm going to be looking at. There was an interesting piece of functionality which was to do with like uninstalling a previous version that was installed. So say you want to like perform an update, you just install your package and they'll go, okay, bye-bye old version, here's the new version. essentially, it had this string, the uninstaller path variable. It initialized it to be an empty string. It then iterated over a hard-coded list of paths. So as you see here, essentially it's using the applications directory. So on a first-time install, that F-secure directory is not going to exist, which is, yeah, interesting. By default, as I said before, users in the admin group, which is not a root user, you still need a password to elevate to root, to use sudo, etc. It's granted read, write, execute to that admin group. Essentially, later on in the script, essentially checks if that uninstaller path variable had been set. So if we had hypothetically placed that application's F-secure uninstall binary there, it would be populated. It then executes that found path with either the P, the U, or no argument. So essentially, you can write a quick little script to just create a malicious C binary or whatever language you want to choose, place it there, and then anticipate a user installing elements. And essentially, like in a home environment, this is like a home antivirus, you're not going to be having a multi-user setup with like identity management or etc. So you just anticipate this install of antivirus. You might have like compromised their emails, etc., seeing they're like getting advertising. Cool. You can get you get the prompt to the admin's putting in his password. You've already set up the exploit chain, and then essentially this root script, text output gets created in an arbitrary location just as a proof of concept. And then yeah, code execution is root from just an install. You have to just set it up and wait for the right moment. Cool. A dangerous assumption was made, assuming an attacker, doesn't have control over a macO in a non-root writable location, which in this case we did. They fixed that by essentially not using the applications directory, which is, yeah, good. Cool. I'm going to cover some unexploitable logic bugs, which are like quite interesting. Logic bugs, you don't necessarily have to exploit them to get root code execution. It's still something that they might reuse code at a later point, or yeah, that kind of mindset. So admin by request, I'm sure people are familiar with it. Like if you're in an enterprise environment and you want to grant your users the ability to elevate a program or a piece of software, essentially this software allows you to do it. Admin by request on macOS, it uses XPC for the privilege separation. It has the should accept new connection routine. Essentially, it has the protocol XPC COM service. If you can see here, it's doing something, set connection code signing requirements, and it has a big code signing requirement string in there. It checks the XPC client, right? Well, not necessarily. So essentially, typically, this is supposed to be, so on macOS, when you sign an app with a developer certificate, it's not officially signed. It's not essentially like proven to be signed by Apple. When you sign something with a dev cert, you have to submit it to Apple, then they cross-sign it, and then you have a properly signed app. Here, essentially it's using or instead of and, which is, I've never seen it before. This is the first piece of software I've seen. So essentially, you can have any code that's signed by Apple, and you can talk to this XPC service. So you think, like, surely Apple don't have any binaries that are vulnerable to DLL injection or DLL hijacking, which is not necessarily wrong, not necessarily right. Essentially, this Safari for WebKit development binary exists on everybody who's got a MacBook here. You'll be able to find this binary on your system. I'm not sure why it's included, but it is. It has those two entitlements that we saw before, the allow dialed environment variables and disable library validation entitlement. So essentially, you can just inject a DLL. Even still, it doesn't have a hardened runtime. Like the flags, none. No hardened runtime, so you don't even need those entitlements. It's a weird binary to be on your system. So you can use the codesign tool to essentially validate if this theory is correct. You specify that connection requirement that we found in the binary, use codesign with the R flag, and then yeah, it says valid on disk, satisfies its designated requirement, explicit requirement satisfied. So what can you do with it? I'm not going to say any more because there might be some fun stuff you can do with that. Cool. So a dangerous assumption was made again, assuming that they've adequately checked the NSXPC client, which they haven't. Cool. Another bug in the AWS client VPN. They had a logic bug in their path checking functionality. Essentially, if you're familiar with like the POSIX file system, like Linux file system, you have symbolic links, you have hard links, and they're like the main type of link you can put. So a symbolic link is essentially a temporary file gets created and points somewhere else. A hard link is essentially the two files need to exist, and a link is placed between the two. Essentially here, all it's doing is just getting the attributes of a target that's passed in like an argument, and then checking if it's NS file type symbolic link, and then does some weird ternary operator because disassemblers aren't perfect. Cool. This is used here and there throughout the service. There's no real files which are controlled by the low privilege user that's like interacted with by a root process, which is interesting. So like this current connection text file and the actual PID file for the like the debug interface for OpenVPN. It's calling is symbolic link, checking if they're symbolic links. Not really sure why it's checking if they're symbolic links. Same here with get valid config path. It's calling is symbolic link twice throughout this. Yeah, not really interesting. You can like test this hypothesis, like how you might be able to bypass this by using a different type of link, so like a hard link instead of a symbolic link. This is research that was done by Csaba Fitzel, and he's got a really good talk about abusing macOS directory permissions. Yeah, highly recommend watching that. So essentially, you can just write some very simple Objective-C. It's overly verbose and like obtuse to make it easier to read. So you copy that ternary operator logic. Essentially, if it's a symbolic link, it shouts at you, is symbolic link bad? If not, it just prints is, and then the type. So we can test that. We create a symbolic link, a true symbolic link, and then run the tool against it. It shouts at us, is symbolic link, and then we create a vanilla hard link with just ln with no parameter, and then essentially it doesn't detect it's a symbolic link. So a dangerous assumption was made here. It's not verifying the file type correctly. If it's really checking if it's a link, it should be checking for extra attributes. I don't know why that's there. Cool, some takeaways. In my humble opinion, don't waste your time with bug bounty if you want to own the bugs, because yeah, I've been absolutely strung out to dry by that. Respect the 90 plus 30 day Google Project Zero rule. Engage with them via email if you want to own the bug. Just don't go through bug bounty programs. Resist the request if they try and reroute you elsewhere. Like, if you want to own the bug, yeah, don't go through bug bounty programs, but yeah, just send it to them via email. If you don't really care, if you just want a bit of cash, just do it through bug bounty programs. Logic bugs are everywhere, some more useful than others. You'll find logic bugs if you just poke at things for long enough. Like, they're absolutely everywhere. Like, great research on like NTFS bugs, like, yeah. Assumptions are made to be broken. Like, if you assume something without verifying it, then you're very likely to be able to bypass that. And computer go brr. Never assume, it makes an arse out of you and me. Or alternatively, I don't know if anybody's watched Lock, Stock, and Two Smoking Barrels. It's a great gangster film, London gangster film. They say, assumption is the mother of all fuck-ups. Cool. Give some credit where credit's due. Csaba and Wojciech, great research. Jonas, Mickey Jin, and Whittaker Labs. It's funny that the guy used this in the previous talk as well, but yeah, cool. Go find some bugs.